and welcome to this lecture on applications of eigenvalues. In the last lecture, we saw how eigenvalues helped us determine stability of linear systems with respect to the, when you look at the operator A, how to use its eigenvalues to determine stability. The absolute value had to be less than 1 for it to be stable and all that. Okay, so that's a good result we saw. So we'll look at another similar application, which is very powerful. I mean, you'll see how why this is extremely powerful as we end this lecture. It leads to this notion of Fourier domain and discrete Fourier transforms. It's very powerful in particularly in electrical engineering, but even in other areas this notion of Fourier domain is extremely powerful, and it naturally comes because of the linear algebraic and eigenvalues involved in systems and their input and output. So in particular, we'll look at discrete time linear systems, linear time invariant systems, and how this Fourier domain sort of naturally enters through that. Okay, so let's get started. The recap is similar to before, so I'll skip it. So let's get into this linear system. So we've seen this before even in the previous lecture, but let me just repeat. So what is a system? In engineering, you think of something that takes in an input, generates an output, has some state, that becomes a system. Many electrical systems work in discrete time, and when they work in discrete time, you can always figure out that my input signal is x0, x1 to xk minus 1 over a period of time, okay, for a certain period of time. Usually you're always interested in a certain period of time. You look at the input signal, you want to study it and put out an output signal. Your system might do something like that, okay. So your output signal y for that period of time is y0, y1 to yk minus 1. Once again, time is discrete, 0, 1, 2, etc. You can think of a clocked discrete time system. It's very common. So this xn and yn could be real or complex also. So complex numbers are just pairs of real numbers with some connections. So we can think of the inputs as being complex as well. Okay, so that's good. That's the setting. And LTI systems or linear time invariant systems are very popular. So most systems that electrical engineering uses, or even in other areas it's used, the output yn will be related to the input x in this fashion. Okay, the fashion is described there. Yn, the output at time n, is given by h0 times xn. What is this h0, h1, etc.? This is called the impulse response of the system. Okay, so you can think of it as some scalars that describe the system. So this h0, h1 to hl are used to specify the LTI system. So once you give me that, okay, the output at time n is simply h0 times xn plus h1 times xn minus 1 plus so on till hl times xn minus l. Okay, so this operation is called linear convolution in electrical engineering. So it's a very simple definition, right? So all you're doing is you take, to generate the output at time n, you take a linear combination of the previous L or L plus 1 input values. How do you do it? You scale each of the values by some constants that you have, add them up and put them out as the output. Okay, seems like a simple way to design systems, but this is very powerful. You can do so many different things with this. Okay, so you can imagine how almost anything that you want to accomplish with system processing of inputs to generate desired output, this you can do. You can do filtering out of some noise, this, that, etc. Averaging you can do. You can imagine so many things are possible with this simple and powerful description. And it's not an exaggeration to say almost all electrical systems at least use this model, exploit this model for design, analysis, etc. Okay, so let's look at this model, and this model naturally leads to the Fourier domain. Okay, so that's what we will see. We will see how eigenvalues sort of enter this picture and then give you the Fourier domain that you need. Okay, so the previous linear convolution can be written as one big matrix transform, y equals h times x. Okay, so y is the entire vector y0 to yk minus 1, x is the entire vector x0 to xk minus 1. I can write a matrix which I have called as h linear, HLIN, which captures this product, right? See, remember y0 is going to be simply h0 times x0. All the previous ones, the x minus 1, x minus 2 and all, we are assuming as 0, right? So system is, there's no input in the time before that. That's something we can do. So we can write like this, and you can see how this h1 enters the picture next, h2 enters also all the way up to hl, and then HL itself will shift. There will be a zeros in the middle, and then you sort of have this circular shift. I mean, not circular, right shift kind of behavior that you have in this matrix. And it's easy to see why this is true. It's the same equation as before, yn equals h0xn plus h1xn minus 1, written in full glory, in some sense every value is written out, and you have this big matrix which represents linear convolution and linear time invariant systems. Okay, given an input signal x, you produce an output signal y. Okay, I'm going to make a change here to this equation. Okay, so I will convert this right shift into a circular type of shift. Okay, why is that important? That gives me a lot of simplifications in the study. It brings in this Fourier and all that. So it's very crucial. And for that, what we will do is we will imagine that this k is under our control. Okay, supposing the number of inputs is not k, something lesser than k, I can always do some zero padding and control this k, increase the input and output length, and that's okay. Okay, so I will imagine something like that. So from x0 to xk, I am not interested in all the k inputs, only up to some point I am interested. After that I have zero padded or something like that. Okay, so we'll assume that. Once you assume that, you can see that I can introduce some additional numbers in this matrix and make it into a circular shift instead of just a right shift with HL to H0. Okay, so particularly in the first part, you see that this is not quite a circular shift. No, the first L plus 1 rows are different from how the remaining rows are working here. So I want to have the same process for the whole thing. So for that, I need to introduce something here on the right top, right? On the right top, I need to introduce something here, and for that I will conveniently assume that I can do some zero padding to do that. Okay, so that's how we move towards this circular convolution. Okay, so if you can assume that there is some zero padding possible, you can convert this linear into circular convolution, and I can introduce these guys here. Okay, so notice this is the part that got introduced. This part got introduced here, and that was not there in the previous linear convolution. Okay, so I have to assume that correspondingly somewhere here, okay, I have zeros, so that this part does not quite enter the picture. So the last few things are not crucial for me, and that's how it works. Okay, so once I do this, it's very simple to describe. So you think of it column wise. Column wise is also very easy. You think of the column is just the impulse response H0, H1 to HL, and the next column is a shift. Okay, and then you keep shifting. If you go below the bottom, you come back to the top. Another way to describe it is, you look at the first row, you write it as H0 and then H1, H2, HL like this, and the next row is a circular right shift. Okay, so from row to row, you simply do one circular right shift to the right. Okay, right shift to the right, of course, right? So row I plus 1 equals circular right shift of row I. Okay, so this is very important. Okay, so such matrices are called circulant matrices. And we see that just because we had a LTI system, okay, and just because we had that convolution operation describing the output for a given input, and we were able to look at a finite number of bits, finite number of symbols, finite number of signals points, right, up capital K, and that was under our control. We could zero pad or do something like that. We are able to get a circulant matrix to represent the input-output operation. Okay, from input to output, the operator that's working on it can be made a circulant matrix. So the circulant matrix is very, very important, because the eigenvalues and eigenvectors of a circulant matrix can be described conveniently in a very nice way and leads very naturally to the Fourier domain. Okay, so let's see that next. So linear maps which are represented by circulant matrices are particularly easy to describe. Why is that? We see that the first column is the impulse response and everything else is circulant. What are the eigenvectors and eigenvalues of CH any circulant matrix? It doesn't matter what the entries of the circulant matrix are, its eigenvectors and eigenvalues can be very, very conveniently described. Okay, so this slide tells you that. Okay, so remember, normally you expect the eigenvectors and eigenvalues to depend on the entries of the matrix. Okay, yes, the eigenvalues in almost all cases will definitely depend on the entries of the matrix, but it turns out for circulant matrices, the eigenvectors do not depend on what you put in the matrix. As long as the matrix is circulant, the eigenvectors are fixed. Okay, So it's a very nice result, and it comes because of the way the operation works, right? So think about what the operation does. The operation simply takes, every row is a circulant shift of the other, okay? So if you want to have an eigenspace for it, if you want to have a one-dimensional invariant subspace for such an operation, your eigenvector, something very simple should happen when it shifts right by one place, right? It should just get scaled by something when it, for every linear shift, every circular shift, it should be scaled by the same value. As long as you have a vector like that, it will become a one-dimensional invariant vector. Okay, so think about why that is true. I would give you the answer here, and then I will expect that you go back and work it out and convince yourself for how this circular right shift operation, okay, can create one-dimensional invariant subspaces. I mean, what is the connection between those two? And all you need is for your eigenvector, when it does a circulant right shift, when a circular shift, it should be scaled by some constant. As long as that is true, it will become an invariant subspace of the the circulant matrix operation. Okay, and that you can guarantee using these roots of unity, complex roots of unity. So complex roots of unity will enter the picture. What are those? I am assuming some familiarity with complex numbers here. We know that this omega that I am writing here, e power I 2 pi by k, is a complex kth root of unity, right? And omega per k will be equal to 1, and there are some nice results like this, like omega per k minus L into k is omega per minus Lk, right? So because it's omega per k times k, omega per k is 1, so, okay, so only omega per minus Lk will be left. So these kind of properties are very important, particularly omega per k being 1 is very important. Okay, so notice what happens now if I define a vector Vk. Notice how this is defined. You have omega per 0 as the first coordinate, omega per k, k can be anything, okay, k is from 0 to k minus 1, some integer, omega per k, omega per 2k, so on till omega per k minus 1 into k, okay. Okay, so I have a length k vector here. What will happen if I do omega per k times k, okay, you will get 1 again, right. So because omega per k times k is 1, okay, so remember that, okay. So now notice what happens if I right circular shift Vk, okay, as in if you do a circular shift on Vk, let me write that down here, circular shift of Vk will simply be, let me do it in some direction, omega per k minus 1 k, omega per 0, omega per k, omega per 2k, so on till omega per k minus 2 times k, isn't it? This is the circular right shift of Vk. If you want, you can do circular left shift also. I mean, both are the same. Now, what is this? If you look at it very carefully, you will see that this is nothing but omega per minus k, okay, times Vk. Okay, do you agree? Okay, the first one is k minus 1 into k, but that is the same as omega per minus k, right? So if you multiply omega per minus k by Vk, you get this circular shift. Okay, so you can also do a left circular shift. You will get omega per k into Vk. Okay, so that is the crucial connection here. Okay, this Vk, because this omega per k is 1, I can define a vector Vk like this, which when circular shifted simply gets scaled. Okay, a circular shift is a scale. Okay, so I put omega per minus k because I did a right shift. If you do a left shift, you will get omega per k. Okay, so circular shifts are scalings for Vk, and you can quite easily prove that for any circular circulant matrix, this Vk will be an eigenvector. Okay, so this becomes an eigenvector. So I will leave the proof as an exercise. It's quite easy, and the central idea is this thing, that the fact that when this circular shifts, you will simply get a scaling for Vk. Okay, and this omega per minus k sort of enters the picture here. So in fact, the eigenvalue lambda k is h0 omega per 0 plus h1 omega per minus k, h2 omega per minus 2k, hl omega per minus lk. All right. So think about why this is true. I'm leaving the full proof as an exercise, and I know there's lots of notation here. This complex kth root of unity and all is entering the picture. Think about it calmly and try and work it out on your own. You will see this happening. And the crucial idea is this: the fact that shifts become scaling for these type of vectors, and that's clearly because this omega per k is 1. Okay, so think about why that worked out. So this complex roots of unity are playing a crucial role here, and you have these eigenvectors. So those of you who are familiar with Fourier transforms will immediately say that lambda k becomes the Fourier transform of the impulse response, right? It's not very surprising. People in electrical engineering must have seen this before, but if you're not from there, maybe you don't quite see the connection, but this is very, very crucial. Okay, so we know, so the crucial point is LTI systems are are characterized by their impulse response, and the input output operation is characterized by multiplication by a circulant matrix. Okay, of course with some zero padding, whatever, all that. Okay, so you have a circulant matrix, and circulant matrices are particularly they have a very interesting eigenstructure. What is the eigenstructure? It's connected to complex kth roots of unity, and you can easily write down an eigenvector, the same eigenvectors for any circulant matrix. The eigenvectors are the same. Okay, and you have different eigenvalues. So notice these Vk in fact are linearly independent. Okay, you can show that these are linearly independent. Okay, so this is also very important. This is these are linearly independent. Okay, so this proof may not be too easy, but you can do it. This is linearly independent. Okay, again that's also an exercise, you can do that. So you have capital K linearly independent eigenvectors for any circulant matrix, irrespective of what the entries in the circulant matrix are. The eigenvectors remain the same, and that's because of this circulant property that this nice vector satisfies because of this complex kth roots of unity. Okay, so this is what you get. All right, so let's see how we can put this to use. Okay, so once you have this notion of the eigen basis, which is the same for any LTI system, whatever LTI system may be, the eigenbasis that I am going to use to describe the operation is the same. Okay, and it's an eigenvector basis. You have a eigenbasis full of eigenvectors for the circulant matrix. Okay, so that's linearly independent set of eigenvectors. That's particularly powerful. Okay, so what people do to go to this so-called frequency domain or Fourier domain is to take your signals and then simply try and express them in the eigenbasis. The eigenbasis is also called the Fourier basis. Okay, the eigenbasis for circulant matrices, you can also call it the Fourier basis. Okay, and that leads to this frequency domain representation for signals. Okay, instead of thinking of the signals as x0, x1, xk, etc., you change coordinates. You change basis. Change basis to what? The eigenbasis of the circulant matrix. Okay, this has tremendous advantages in describing what the LTI system is going to do. Okay, so we'll see that soon enough. But how do you do that? It's easy to see. The matrix to go from Fourier basis to standard basis is simply this. Okay, standard basis is what people call time domain. Fourier basis is this frequency domain. How do you go from Fourier to standard basis? You simply multiply by this matrix, and this is called IDFT-K. Okay, so this is a very popular matrix. It's called inverse discrete Fourier transform matrix of size k by k. I've put this 1 by root k here. I mean, it's just for convenience. It's not so crucial, but this is the operator which will take you from the Fourier basis to the standard basis. Okay, so basically this leads to the definition of this discrete Fourier transform of signals xy. It's nothing but the xy which was given in standard basis or time domain expressed in the Fourier basis or frequency domain. Okay, so the notation one can use is x hat. Okay, the Fourier basis represent coordinates of x. I will call it x hat 0 to x hat k minus 1. Y hat is y hat 0 to y hat k minus 1. How do you go from x hat to x? You simply multiply by IDFT. Okay, going from x hat to x is multiplying by IDFT. How will you go from x to x hat? You have to multiply by the inverse of this matrix. It turns out the inverse of this matrix can be very easily found, and that's called the DFT matrix. Okay, matrix to convert from standard basis to Fourier basis, it's the DFT matrix. Instead of omega, you will have omega power minus 1. You can imagine. Okay, so why this has to be true is properties of this complex kth roots of unity are such that this is the inverse of IDFT. Okay, and the 1 by root k also works conveniently for us to give the proper inverse. Okay, So what people do when they want to study LTI systems is not only use the time domain or just the signal domain representation. For the input, output and impulse response, people convert this x, y and h from time domain or standard basis to frequency domain of Fourier basis. How do you do that? X hat is dftk into x, y hat is dftk into y, h hat is dftk into h. Okay, you may argue h has only length up to n, you have to zero pad. Okay, so you do zero padding to convert the length to k, okay, so that you can use dftk here. Okay. So once you do that, what will happen in the Fourier domain? In the Fourier domain, the circular matrix becomes a diagonal matrix. What occurs on the diagonal? The lambda k. What is lambda k? It's nothing but h hat. Okay. So h hat 1 to h hat k will occur on the diagonal for this h circulant. Okay. And you see yk hat is xk hat into hk hat. Okay. So h circulant is diagonalizable. It has a full set of eigenvectors, in full linearly independent set of eigenvectors, and that gives rise to this whole Fourier domain or frequency domain business of studying LTI systems. Okay, so instead of worrying about a complex convolution with multiplying, scaling, addition and all that, once you go to the Fourier domain, it's only multiplication. Your H circulant became just a diagonal matrix. Okay, and that's the powerful thing. And not only that, it doesn't matter what the impulse response is. As long as it's circulant, the Fourier basis is fixed. So it's very powerful. Okay, so you take any signal, you write it in Fourier basis, you will get an idea of what's going to happen to it when it goes into the LTI system. So instead of looking at the impulse response, you want to look at the frequency domain representation or the Fourier basis representation for the impulse response. You get a sense of what it does to the different eigenvectors, in the eigenvector basis. So the eigenvector basis gives you a fantastic grasp of how the whole LTI system works. Okay, so this is put to heavy use in electrical engineering. Many subjects in electrical engineering talk about frequency domain, its various properties, how do the coordinates behave in frequency domain with respect to the coordinates in time domain. Okay, so many nice problems can be phrased, and this behavior, if you do something to the time domain, something will happen in the frequency domain. It's all of that can be quite easily derived and understood, and they are used quite extensively. Okay. So this notion of eigenbasis representation to simplify the operator is very, very, very crucial. Look at how we used it. Okay, the H circulant otherwise was having a very complicated looking matrix. We went into the Fourier domain or the eigenbasis domain. We got a very simple diagonal matrix, and that's been used very heavily in applications in electrical engineering. Okay, so hopefully this again convinced you that this eigenbasis representation is not some idle theory. It's very, very powerful, and it's used quite a bit in engineering. Okay, thank you.